Let me extend a question to you guys. Yeah, lucky 7. Lucky 7, there you go. Yep, it just occurs more often. 14's even out now, very nice. So I want to go back to what Tabitha said beautifully. Outliers are unusual or atypical. And I want to tie into that what Athena said, and a couple other folks agreed with. Atypical means it shouldn't happen very often, which means the probabilities are less likely. Define less likely. Which of these outcomes, oops, I didn't want that to go all the way out. Which of these outcomes would you say are unlikely outcomes? If you had to pick them, list them off. Which ones would you say are unlikely? I'll just hold it, that's fine. 2 and 12 are unlikely. Good. How about 3? What do you got 3?
Yeah, it's still a little unlikely.
Still a little bit unlikely, not as much as 2, obviously, right?
Yeah.
How about 4? Now, 4 is, that's almost 10% of the time. That's 1 in 10. That's pretty high, isn't it?
Yeah.
So if you're saying 4 is okay, I'm guessing 5, 6, 7, 8, 9 are okay too. 10, if you're okay with 4, I guess you're okay with 10, right? So basically what I'm hearing is, you guys definitely think that snake eyes and boxcars is pretty unlikely. And you're kind of like, with 3 and 11, you're kind of like, maybe, maybe not. Check this out. This is almost bell-shaped data, right? Almost bell-shaped data. Bell-shaped data, we can use that cool empirical rule, can't we? What does the empirical rule say? 2 standard deviations from average captures 95% of the data. Remember that? Remember that bad boy? 2 standard deviations captures 2 standard deviations from average. Well, for standard deviation, this is about 2.5, isn't it? We don't have to. We're going to do this conversationally and then bring it back to something even easier than box and whisker plots. You could, for sure. You could make a box and whisker just like Tabitha did back there with her quartiles. You totally can. But let's just do it conversationally. If I double that, 2 standard deviations, okay? If I do mu plus or minus 2 sigmas, I'm going to get 7 plus or minus roughly 5, or not 5, roughly, we'll call it 4.8. 4.8, okay? If I subtract 4.8 from 7, I'm going to get 2.2, and if I add it, I'm going to get 11.8. That would be 2 standard deviations from average right there.
Not quite 2, not quite 12.
Nice. What that means is 2 is underneath typical, which you guys just said 2 was unusual, and you said 12 is too big for typical, and you guys said 12 was unusual. And you guys said, yeah, but 3 and 11 are too hard to call. Well, check it out. 3 and 11 are very, very close, if you will, to these values right here. They're getting close. I mean, they're 0.8 off each way. Everything else is well contained. So what you guys just kind of showed is you have an intuitive understanding of what's actually going on with this. These are definitely too small. Those are arguable. And believe it or not, your intuition actually is supported scientifically. In every research journal you've ever read, basically, rarely happens an outlier in the biz, if you will, in research journals, in scientific journals. An outlier is defined as any event happening less than 5% of the time. So basically, this is my favorite definition of an outlier. My favorite definition of an outlier. Look at the distribution of probabilities. Find the ones that rarely happen. Those are the outliers. And to quantify it, the outliers are going to happen less than 5% of the time. To give you a quantification of that. That's the beauty of having a distribution. Not only that, but going back to what Tabitha said about 5 minutes ago, too big or too small just becomes too rare, too atypical, or not typical enough. This means outliers can actually pop up in the middle of distributions if they're bimodal. If you have a bimodal distribution or a trimodal distribution, you have those valleys between the peaks. Those valleys might be outliers. You may have an average here and an average here with this belly in the middle. That won't be within 2 standard deviations. Or it won't be outside of 2 standard deviations, but it will have a small probability, which means it's unusual. Love that. It's beautiful. Kind of makes sense-ish in there? Just one more definition, but it's not like it's one more, it's just an extension of what you already knew. It ties in beautifully with all the other definitions that we've been talking about. Fair? All right, this is great. This is fantastic. But what I want to do with the remainder of the time we have is I want to analyze how this is more generally applicable to what we experience on a day-to-day basis. And when I talk about that, I'm talking about things like insurance rates, things you have to pay for, which are all based on these probabilities. I mean, you guys have to carry car insurance, you have to carry, maybe you carry health insurance. All these insurance rates, the values you pay are somehow based on likelihoods of something happening. Getting in an accident, not getting an accident. Getting sick, not getting sick. You pay more when you're a smoker for health insurance. Why? Why?
You're more likely to die when you smoke.
Because you're more likely to have, let's just make it more general, you're more likely to have health issues when you smoke. You're more likely to have health issues when you smoke. Maybe die too, maybe die too. So what I want to do is I want to start with a pure gambling example, and then tie it into an insurance example, if that's okay with you guys. So, let me pull this down, and I'm going to show you the rules of a fun little casino game. I have to find it here. Here it is. Called Chuck-a-Luck. This is one of my favorites.
Is that 2 point?
Say that again. 2.4? So I doubled it, 2 sigmas.
Oh, that's an S, okay.
Well, it's a sigma. It's a Greek letter. The Greek, remember, there is no S for this guy.
Okay.
Because it's a population.
That's why I can't understand it.
No, listen. And you know what? Don't even worry about it. Don't even worry about Cassie. Look at this. Which ones of these are less than 5%? Less than 5%? Less than 5%? There are your outliers. Fair?
Yeah.
Good. All I'm trying to do is compare and contrast with what you already knew
Right.
and show how it falls in line beautifully with it. That's all. Didn't get confused. All right, let's fire this up here. No, not free screen. Blank screen dot cam. Yay for us being all. Yay! Here we go. This is a little bit of gambling we're talking about. It's a game called Chuck-a-Luck. Now, every casino game operates on the same principle. You go into a casino, they give you free drinks, you give them money. Basically, the basic idea behind Vegas and why they keep their lights on all the time. Basically. What I want to do today is start having you guys understand how to analyze the games. So Chuck-a-Luck's an old school game. It was more popular in England, I think. There's still Chuck-a-Luck boards around in Vegas. But I like Chuck-a-Luck because it drives home the point of what we're doing right now beautifully, but it doesn't get convoluted in the bets like games like craps do. Games like craps are great because there's one probability to focus on, but the betting is so annoying. So here, it's very simple. You walk up to the table, see that thing at the top called a bird cage. Bird cage is a little roller thing that has 3 dice in it. You take $1. Let's just say you bet $1. That's called your ante, your bet. You walk up and you slap $1 down. And you put your dollar on one of those 6 numbers. Let's just say you bet on 5. It doesn't matter which one you bet on because they're all equally likely to come up. You bet on 5, you put your dollar down. If then the nice person behind the desk spins the bird cage and you see any 5 come up, you win something. And here's the way the rules work. If you get exactly 1 5 out of the 3 dice, you win $1 back. Now you paid $1 to play, you win $1 back, that means you broke even, you're a 0. Fair?
You are a 0, okay.
Well, no, you should break even, right, Kevin?
Yes.
Saucy today she is.
Yes, sir.
Now, suppose you get 2 5s and something else, like 2 5s and a 6 or 2 5s and a 1. Then you'll get $2 back, which means you've cleared 1. You bet 1 to play, you win $2 back, therefore you've cleared $1. And the jackpot is, if you bet on 5, and you get 3 5s, they give you 10 to 1 payout. So if you bet $1, they're going to hand you $10, which means you clear 9. Now, if you don't get any 5s, you lose $1 you play. You put the dollar on the table, they take it away from you, and you walk away. Or you play again, depends on what you want to do. The question I have is, what do you win on average playing this game? What do you win on average? If you play this game over and over and over again, what would you expect to win per game? That's what I want to talk about now. You're going to lose your shirt. Okay, there's a vote. We're going to lose our shirt. Say again, would it be the same?
It would be the same for each number.
Yes, it would not matter. Tabitha, that's a great question. Tabitha's question is, would it matter what number you bet on? It would not. Think about it this way. If you bet on 5, there's one way to get 3 5s, 5 5 5. There's also one way to get 3 6s, 6 6 6, 4 4 4. It doesn't matter what number you pick. You can also split. I believe there's different ways to split. That you can bet like $3 and put a number on each or something like that. The payouts change though. So I'm going to keep the payout simple to the one betting strategy, which is $1 laid on the number 5. How are we going to do? Is that fair? So that's what I want to analyze right now. So I have one vote for lose your shirt. I like that. That's a good
It's
one.
like Funko.
I don't know how Bunko works, but we'll have to come back to that one too. Maybe we'll bring the next quiz out of Bunko. I keep hearing about Bunko. I never heard about it until I moved out west. Very, very good. So here's example 3. Chuck-a-Luck. Now, honestly, we're going to have to build the distribution for this. We are. We're going to have to build the distribution for this bad boy. But the only reason we want to build a distribution for it really is to answer the question, what are your average winnings in a game of Chuck-a-Luck? And when I talk about average winnings, I mean over time. What are you going to win? I put winnings in quotes.
So you got 3 dice.
We got 3 dice.
So before we had 2 dice.
We had 2 dice before, so there were...
6 possibilities. So you have 6 times 3 times, or 6 times 6 times 6.
You have 6 cubed possibilities. There's 216 possibilities for this.
Right.
I'm going to encourage us not to worry about trying to figure these out the way we figured out 2 dice. Because this is where the exponentially harder. First of all, I don't have a good visual to show the 3 outcomes like I would need a 3 outcome. So I have a simulator to give us the probabilities that we're going to need. But before we even get there, I know we need to build this distribution. We've got to build the possibility of all possible outcomes, right? So I'm going to make this be the amount that we're going to win in this game, or the amount we won. And we need a probability column over here. So we have to figure out these things right here. I'm going to add 1 column just to help us out. This is not part of the distribution at all, friends. I'm going to add a column over here, though. This is going to be number of 5s that were rolled. This is going to help us decide how much money we win. So if you bet on 5, how many 5s can come up on the dice? 3 or
0.
Or 0 or 2 or 1. So basically we have 0, 1, 2, and 3 possibles for the number of 5s that came up.
Okay, so you can get -1.
Very
0.
nice. If you don't get any 5s, you're going to lose $1. If you get exactly 1 5, how are you going to do?
Break even.
You're going to break even, exactly. So you get $0. Because you bet $1, you're going to $1 back, washes. If you roll 2 5s out of 3,
$1.
you clear $1, don't you? You clear $1. And if you roll all 3 5s,
$10.
but you clear 9, exactly. You clear 9. You win 10, but you have to take the ante out for the $1 bet. Beautiful. These are our data now. These are our data. Now, if I asked you on average, how are you doing? Could you just add these numbers up and divide by 4 and say, holy crap, we're going to make 225 on average?
No, because think of all the other pairs that are working against you to not get your stuff.
That's the kicker. This is where most Americans would goof this up. They look at that distribution and go, holy crap, there's 4 outcomes. A 9, a 1, a 0, and a -1. If I add all 4 of those together, it adds to 9. Divided by 4 is 225. I'm going to average 225 per game. If it was just as likely to get that as that, as that, as that. But you know that's not true.
Now you've got 3 crappy ones and 1 good one.
You've got,
You're gonna land
yes,
on
and which ones are most likely?
the crappy ones.
How likely are they? What goes
5
here?
to 1.
Gut feeling. How likely is it to lose that $1? What do you guys think? What probability should go here?
Probably like 10 to 1.
10 to 1 being 10%. So 10%, so this is going to add to 90%. You're calling this 10%. This is going to be 90%.
Yeah.
So what's this itself going to be? What's the chance of losing? Because you win something here, don't you?
You have 5.
Oh, I see what you're saying, Raphael. So you're saying it's 10 to 1. These 3 add to 10%. Give it a 90% chance of losing.
Yeah.
So we have a vote for 90%. 90%? What do you think? 90%? Tabitha?
Pretty good. Well, if we were gonna do 6 cubes, wouldn't it be 216?
216 is the sample space, my friend. I love that, by the way. Thank you.
So if the sample
Oh, really?
No, this is great. And the reason, Tabitha, thank you for proving my point. I've thought about this a lot. I used to try to get those numbers filled in exactly like the 2 dice case over here back in the day, but it drives students nuts at this stage in the game. There are 216 possibilities. And this one, you know what this one's going to be right here. 1 out of 216. Roughly 1 in 200, which is roughly a half of 1%.
Well, you figure you have 3 dice,
Yes.
and there's 5 other numbers on each die.
There's 6 numbers total on all
But
the
there's
dice, right?
5 that are going to be wrong.
That are going to be wrong. So what's that first space going to be there, Dina?
5,
5
5 to the third.
5 to the third, 125 out of 216. Hold that thought. Would you hold that thought, my friend? Please, if you don't mind.
You might want to write it down.
Don't worry, I'll remember it. It's awesome. I'm so proud of you for picking. That's exactly right. What Athena just figured out is, yes, we can figure out the 1 and 216 in the bottom and the 125 and 216 in the top.
If you're going to fight, how many people? You got 3 people on your side, and all the rest are not.
Okay, well, that's kind of an interesting way of thinking about it. Yes, correct. Very correct. But refreshing.
Take my wallet.
What I'm going to do instead, friends, is I'm going to simulate it using Excel.
Yay!
I promise you though, we will come back to this when we have a tool called the binomial
There's a
distribution.
reason I don't gamble.
Now, no, please, I will say this again, public service announcement. I am not telling you not to gamble. All I'm trying to do is give you the tools to analyze the results of what's going to happen. That's all I'm trying to do. I'm not trying to say don't have a good time in a casino.
You go in.
When do you ever have a good time in a casino?
I don't know, I don't go myself.
I am sorry, but
I'm going to see Tesla on Friday and Chinook wins. Maybe I'm going to have a field day in there, I
There's
think.
those people that win money at the casino
Friends.
constantly.
Look at this. Look at this.
Who are they?
Look at this.
What?
Remember what Shelby said about the probability, Kelsey, excuse me, Shelby, Kelsey, one of you guys. The probability of hitting this, getting all 3 5s, was 1 in 216. There's only one way to do it, 5, 5, 5. 1 in 216 is 0.005. Look how close that's coming. Every 216 rolls, we should be seeing one of those. On average, right? On average, that's not here, I can't point to it. Over time, on average. So every 216, roughly every 200. So now we're up to about, we should have seen about 10 of them. Holy crap, about 11 of them. Look, 2,200? About 11. That's doing exactly what it said. We heard 125 out of 216 over here, which is the correct probability for this guy right here. And that's going to work out to just about 60%. Look at that. The tricky ones are the ones in the middle. And we'll come back to those with my chicken flock next week because that's the easiest way to analyze what goes on in the middle too. We'll come back. I promise we'll come back to those guys. I promise we'll come back to those guys. But right now, I just want to use these numbers to analyze our game. Roughly, you're going to win this game. You're going to win, or excuse me, you're going to lose this game roughly 60% of the time, which is actually better than you said, Raphael. You say 10 to 1 against. It's more like 6 to 4 against. Which is still, you're losing more than you're winning, for sure. But you're not losing anywhere near as much, and that's what makes a good gambling game. Let people win enough to keep them playing. If you make them lose 9 times out of 10, they're going to stop playing the game. So design the game to let them win, but don't win a whole lot. Make sense?
Yeah, you just keep them
Enticed.
Exactly. Keep them enticed. Keep them throwing their money at you, right? Good. So let's just stop this, and let's use, notice how they've kind of stabilized, the numbers have kind of stabilized now? Let's just use those as our values. The chance of losing the game is roughly 0.591. So 59.1% of the time you're going to lose the game. The chance of rolling exactly 1-5 appears to be 0.337. Winning 2 5s is 0.069.
Which is ridiculous.
And well, this is one, remember, this is all winning right here, Athena. All these are winning.
Yeah, but look how much you lose compared to.
Well, that's what we're about to, we need to answer that question.
I don't
The
count
question
keeping my
is,
dollars
what is
winning.
the average that we're going to end up with, right?
Yeah, but I don't count keeping my dollar as winning.
Hang tight. You got something back though.
Whatever.
When you look at the casinos and you're playing $3
I
slots,
can't go
and the machine says 98% of the time this machine pays out, they're counting the fact that you paid $3 and it gave you a quarter back as a payout. It's all about the definitions, friends. It's all about how you define it. And last but not least, this guy 0.004.
I go to Vegas to shop. I make sure
That's
I go
quite all
back.
right. I'm not trying to be critical or depressing, just elucidating. That's all. I'm not hallucinating, elucidating. Look it up, Raphael. I'm not making this one up either. And I got you back there, buddy. All right. Now, what I want to do is, I want to calculate this average, but I don't want to use one bar stats on it. I want to actually do this one out. Old school, because I want you to see the components. Athena, you brought up a very good point. This is why I want to do this old school. In other words, as a weighted average, like we used to do back in the day. So let's clear a little bit of room. Let's draw a little line from over there. It's not that much. It's not that terrible of a calculation. So, average winnings, let's bring this over. So, in order to calculate the average of any random variable, you have to add up the product of the data and the probability of each of those data points. And the reason why I want to do this out and not use the TIs is because I want you to see the actual individual pieces and understand what each piece is doing. It's very, very important, I think, in a case like this. So we take the first data point, which is -1, and that's -$1. times the likelihood of losing that, which is 0.591. What that tells us is 59.1% of the time we lose $1. That's all that means. Plus,
How many times do we break even?
yes, we break even 33.7% of the time, which is more than half of when we lose. Okay? That's what's really keeping you in the game right there.
We're not even winning.
Hang tight, hang tight,
We're not
hang
even
tight.
winning a quarter of the
Hang
time.
tight, hang tight, getting there. Now let's get the pluses in. 6.9% of the time, we're going to win $1. More space. And last but not least, 0.004. Oh, let me do the correct order. We're going to win $9. Okay, so take a look at that. This is important. Okay, so 59.1% of the time, we lose $1. 33.7% of the time, we break even. 6.9% of the time, we win $1. And 4 in 1,000, we're going to end up winning $9. Those components added together give you your overall average winnings. So this is 0. That just goes to 0. This is 0.069. That's 0.036, right?
This is your overall,
Yes, this is in dollars.
right, this isn't weighted. This
Yes,
is-
the weights are right here, Raphael.
Right, we can do that independently.
Exactly. So we're doing the pieces individually. So from right here, we win about 6.9 cents, 7 cents on
For
average.
every buck,
Right? Here we go. Good. Hold that thought, Athena. Right here, you've got 0.036 cents. Here, this is 0. And here, you've got negative 59.1 cents. So you lose this, but you gain a little bit of it back over there on those other trials. But you're only gaining back, what? About 10 cents-ish?
for every 60 cents they take from you, they say, all right.
What does this sound to be? What do you got, Cassie? 46 cents? Which means your average winnings in Chuckaluck is negative 46 cents, which means on average you're losing 46 cents. Now, it is impossible for you to lose 46 cents at this game.
Right, because you have to throw in at least $1.
Right, if you're going to lose,
But it's an average.
you're either going to lose $1 or you're going to break even. Negative 46, look where negative 46 falls, friends. It falls directly between, in the distribution, negative 46 basically falls directly between these two. And that's how they get you. Half the time you're breaking even, half the time you're losing money, and every once in a blue moon, you end up down here. Did you see that? Friends, did you see that in the Excel simulation? Watch that red box. This is a genius game for this point. Watch that red box as we're, I think it's still randomizing. I think the stapler's still on there.
We're having a fundraiser for schools.
You have to pick that game?
No, I gotta pick that game so we can.
Okay, you ready?
School
This
fundraiser.
is fantastic. Watch that red box. What do you see almost all the time? Zeros and ones. That's what makes it a brilliant game. The ones are hitting, every once in a while it's out of them. A two blows in, a two blows in. You miss the threes. The threes go by so quickly. Watch. I think one just happened. But you're getting so many zeros and ones. And that's what's keeping the average right about at negative 0.5. You're losing 50 cents for every dollar played. So essentially, rather than playing the game, just walk up to the counter and hand the person 50 cents and walk away. That's what's happening, right? Essentially. Now, that's never actually happening, but on average, that's what's happening. Does that make sense? And that's the beauty of it.
If you want to stand there and play, you gotta figure it's gonna cost you 50 cents.
And then you have to ask yourself, is that worth the pure entertainment value of
How
playing the
long
game?
if it's
Maybe,
one game?
maybe. Again, I'm not trying to tell you not to gamble. I'm just trying to give you the tools to analyze the results.
Well, if you're only paying 50 cents for the drinks they're bringing you.
Well, then there you go. If they're bringing the drinks for free, then maybe that's a good deal,
How
right?
long does it take you to
Maybe
get?
that's a good deal.
If it takes you 15 minutes to take a drink, and it only takes 30 seconds to play a game. So
You
you're
see?
times 50.
Now you've got the tool to analyze that, don't you?
That drink doesn't cost you.
Now you got the tool to analyze it. Grab one of these and hand it back, my friends. What I've got here, friends, I want to do one more distribution. Actually, there's a couple more examples, but there's one that I really want to look at with the remainder of the time we have together. I'll let this guy play all day, but I think you're seeing the point. I think you're seeing the point of this. Okay.
How long does it take to sucks to
Yeah,
get?
so you gotta look.
No! I'm not saying that. I'm saying, no, they're fine, you know what I'm saying. Now here's what I want to do. What I want to do, last but not least, is I want to analyze how this actually ties into a non-gambling, non-dice, non-coins, non-card kind of example. And it's all about insurance. And I'm talking in particular with this one about life and disability insurance. What I did was I entered my information. I think this was last year. Oh, thank you, Jessica. I entered my information into a CDC insurance rate, or not insurance rate, likelihood calculator. And I put my age, where I live, my kind of like, I'm a bike commuter, this kind of thing, that kind of thing. And it told me that I have a 0.00269 chance of dying within the year. That's my chance of dying according to the CDC. If you see that in number 2 right there? So my chance of dying within the year, 0.00269.
They have that on the CDC?
They do. Well, I had to kind of dig for it, but they have like a little like life expectancy calculator kind of
Oh,
thing.
how do you do that?
That's super fun, super fun. I wish I had the link on here for you.
So one in something.
So basically, it's if you will, 3 in 1,000. Round the 2